Hello guys, today we're looking at the intermediate geometry problems on aops, and I'm just going to do the first two today. So the first one, we have this triangle ABC, and then it gave us the ratio of the sides, so I already got them out on the drawing board. As you can see, it's 2 to 2, 2 to 1, 2 to 1, 2 to 1 on the three sides, and then 3 to 3 to 1, 3 to 3 to 1, and 3 to 3 to 1 on the three chords. And then we're trying to find the ratio between the area of the central triangle to the area of the large triangle. So how do you do that? First of all, let's notice that since we're trying to find the area, we can probably first get some ratio of the areas by using the line segments that they gave us in the diagram. And if I come up, find my cursor, oh, it's right here. The area between any of these two triangles, right? For example, these two, or maybe these two. There's three pairs of these triangles, and it's obvious that their area ratios are all 1 to 2 because of the same height and different base, and the base ratio is 1 to 2, so the area are all 1 to 2, these three pairs. And we can also notice that, say, let's first find the area of ADC to the area of the big triangle ABC. That's obviously 1/3 of ABC's area. And then we also notice that since the ratio of the base between AN1 and N1D is 1 to 6, the area of the triangle N1DC, this tiny one here, is just going to be 1/7 times 1/3. So that is going to give us 1/21st, right? 1/21. That is the area. And then notice that we can do this exact same operation to the other three triangles, the other two small triangles on the tip, and they're all going to be 1/21 of the big ABC. And then we also notice that the area of F and this quadrilateral F and 3 and 2A is going to add up to 7/21st. Like, no, this whole triangle is 7/21st, and the quadrilateral that I just said is actually going to be 7/21st minus the 2 1/21st, so 5/21st, right? Obviously, because this triangle is 1/3, and 1/3 is just 7/21st. So 7/21st minus 2/21st of the two triangles on the tip. And notice we can do this exact same operation to 5/21st. Notice we can do the exact same operation also to these two quadrilaterals. So we can get two more 5/21st. Right? Even though my handwriting is kind of bad. And then notice that we can now just add up all the ratios of every single part we found other than the one we want, right? Everything else we found. So we just take one, subtract all the other ones, which all the other ones are going to add up to 18/21st, which is just 6/7, which 6/7 obviously. And then 1 minus 6/7, we get 1/7 for the area. So that is the solution. Okay, and that is the answer to this problem. Now we take a look at the second one. It's the AHM SME problem 40 this time. And okay, first let's take a screenshot so I can put it on the drawing board. Okay. This time we're still given the triangle ABC. Yeah, most of the geometry problems are just triangles, and it also gave us a few ratios. We have BD as the median. BD, yep. Okay, so AD equals DC, and then CF intersects BD, so that BE equals ED. So we have ratio 1, 1, also like that, right? And now I know GD sort of made because I took the screenshot from a graph of the solution, but we actually don't even need GD in two of the three solutions that I'm going to present today. So first of all, let's look at a solution that does use GD as an arbitrary line that we make. So, well, obviously, this is a triangle, obviously, but we also notice that since these edges are equal and these two are equal, we can make the GD parallel to EF and FE, and FE FE is just the median of this triangle. Now that we know uh, FE is 1/2 of GD, we can also notice that ACF is another triangle with GD as the median, because obviously we already know that FE is parallel to GD from knowing it's a median, and we also know that AD is equal to DC, so obviously GD is the median of ACF. So now we also know that not only is FB equal to FG, but FG is also equal to GA, so obviously we have 5, 5, and 5. AB is just going to be 5 plus 5 plus 5, 15. However, there's another way that we don't even need to make the line GD. So we already know BE is equal to ED and AD is equal to DC. We can just use a simple trick called mass point. Mass point is basically kind of like physics, in which we induce the concept of levers into math. So say, let's give the point B a mass of 2. Then to make the lever balance, if the fulcrum is at this point, E, then D has to also have a weight of 2, because the length of these two arms are the exact same. So to make it balance, D must also have a mass of 2. And also to balance the weight of A and C, because we know AD is equal to DC and the fulcrum is at D, then we have to make all of them the same way and a total weight of 1, because D is the center of mass, so D has to be the sum of the mass at A and C. So they add up to 2, so only 1 and 1 add up to 2 and are equal in weight, so obviously A has a weight of 1. And now that we know A has a weight of 1, B has a weight of 2, taking F as the fulcrum, we can easily tell that this is 1 and this is 1. No, sorry. The ratio is 1 to 2. So the actual length is going to be, this is 5 and this is 5. So that is another way to do this using mass points. However, there's one more way actually to do this using area. So, okay, I'm missing a dash, I just noticed. So since we know AD is equal to DC, the area of ADB is going to be equal to the area of BDC, right? And then if we make an arbitrary line from A to E, we notice that, okay, also since ABD is half, BDC is half of the big triangle ABC, and BE is equal to ED, so this is 1/4 of the big triangle, and this is also 1/4 of the big triangle. And we also know that since these two lines are equal and equal height, obviously, we also get that AED is also 1/4 of the small triangle. And according to a very well-known theorem, I don't remember what it's called, but we have, since we have point F, BEC has an area proportional to AEC as the same as the proportion of BF to FA. I'm going to use a different color so we can visualize it more. Basically, we have BDC, the area of that, and FB is going to be proportional to ACE and FA. And since we know this is 1/4, this is 2/4, then the ratio between BF and FA is just going to be 1 to 2, so the whole length is just 15. Okay, and that is how you solve the 1959 AHSME problem 40, which is the second one on intermediate geometry problems. So yeah, that is the video for today. And I know I haven't posted in a while, and I said I'll post one every single day, but I just didn't find any time really. So I guess this is a better style to record than actually using my iPad, because this makes it easier for me, and I'm more motivated to actually do videos now. So yeah, okay, thanks for watching, and hopefully I'll see you tomorrow.